In over 30 years of machine vision experience, I've seen and experienced many challenges, and I've learned techniques to help control these problems. For example, have you ever done a feasibility study in a lab and then built a system, but the system you built didn't perform as well as your feasibility study? Or how about having a system in the field that works well? You build a copy, but the copy doesn't perform as well. Or you have a system that works well in the field, but over time its performance degrades. The common thread is probably something that has changed in the imaging. In my talk, I'm going to discuss a technique, actually a series of techniques, that you can adopt that'll help you control these kind of situations. It's inexpensive, it's quick, and it's uncomplicated. There are 10 measurements that you can make on the imaging system that I call benchmarking the imaging. There are 10 parameters that you should benchmark that will allow you to recreate your imaging. Now, sometimes you don't need all 10, and sometimes in specialized situations you will realize one or two additional parameters that you should benchmark to keep your imaging under control. Before you begin your benchmarking measurements, make sure you record all of the components, dimensions, and settings of your vision system. Now, if this is a well-documented vision system, your bill of materials will list all of the components, and your mechanical drawings should show all of the critical dimensions. However, if this is a laboratory system, you will have to make a list of every component, make, model, and option, and measure and record all of the dimensions, including angles. Today's vision components are often very programmable. You will have to record all of the settings. For the light source, this might include the power and the pulse duration. For the lens, at a minimum, you need to record the aperture and focus setting. And today's cameras are quite programmable. Make sure you note the mode, exposure time, gain, offset, and anything else that can change. Oh, and our best ally in documenting a vision system is the digital camera. It's quick and inexpensive. Take lots of pictures and print out these pictures and put them in your binder. Or at least I like to keep all of my imaging notes together in a small, thin binder. This makes it easy for later reference. But also, all of your images should go on a CD so that you can evaluate them later on a computer. Earlier, I did some work in the laboratory demonstrating some of the benchmark measurements. Let's go there now. Here we have a very simple demonstration system. It consists of a light source, a camera and lens, and a computer. After recording the settings of the vision system, the first thing we want to benchmark is the size of the field of view. I'll show you two ways to do that. The first way uses a machinist scale or a precision ruler. I can carefully position the ruler so it spans the field of view. Then I can read off from the ruler the dimensions of the field of view. Now you may wonder how accurately you need to measure the field of view size. Well, keep in mind the effective focal length of most lenses is only within a tolerance of plus or minus 3% of the specification. So unless you are performing extremely demanding scientific work, what you can read from a good ruler is sufficient for benchmarking. You will want to record the field of view dimension in your binder. Also, it's a very good idea to capture, print out, and save the image of the ruler as a means of avoiding any future questions. Now repeat the measurement for the other size of the field of view. For very small fields of view, a ruler may not be practical or may not have the resolution you need. In those cases, you can buy a commercial reticle with very fine gradations. The one shown here is good for a field of view of perhaps 15 to maybe 20 millimeters. A convenient way to check the field of view is to make your own target using a CAD program or drawing program of your choice. You can print that out on a good quality laser printer, and you come out with a target that looks something like this. Now, this target has the corners of a rectangle that define the expected field of view. The dot pattern inside can be used for calibration. Just remember that the laser printer is not traceable to any standards lab, and paper is not necessarily dimensionally stable. We place the field of view target in position and center it in the field of view. The image shows how well our actual field of view matches the expected field of view. An advantage of the target over the ruler is that you can fixture it in place. That way you can benchmark not only the size of the field of view, but its alignment as well. Now, keep in mind that precision isn't required in this benchmark, because if there are variations in the size of the field of view, calibration will correct for any variances in magnification. When you finish the benchmark, be sure that you record it in your notes. And keep a copy of the images, both on DVD and on a hard printout, which you can put in with your other notes. Now, you should already know the spatial resolution of your vision system. The spatial resolution is the spacing of pixels on your object. Now, suppose you make a target of alternating light and dark bars, and the width of each dark bar and each light bar is exactly equal to your spatial resolution. Now, if you put this target in your field of view and you carefully align it so that each bar is imaged by just one column of pixels, you would have the best possible resolution your vision system could give you. However, if we move this target just a little bit, just half a bar's width to the side, what we get is a uniform shade of gray out of our vision system. This is a critical spacing called the Nyquist frequency or the Nyquist criteria. We really can't hope to resolve detail this fine or finer with a vision system. For your target, use a drawing program or a CAD program to make a series of bar patterns. Each pattern, the bars are slightly wider than the ones before. I recommend at least 5 bar patterns. For 5 bar patterns, each bar pattern should be 1.189 times as wide as the previous pattern. The final or 5th pattern, the bars will be twice as wide as the original pattern. If your system can't resolve this bar pattern, then the lens is severely limiting your imaging. Now let's return to the lab to see how we'd use this in practice. Here is the image of the resolution target shown in the monitor. The image sensor resolution, the quality of the lens, and the aperture setting all combine to affect the imaging resolution. You should have documented the components and settings to make sure the system is correctly set up for you to measure the image resolution. Now, you measure the resolution by observing the bar pattern that is resolved in the image. Note the smallest bar pattern. And you need to measure this not only in the center, where the imaging resolution is typically the best, but out at the corners of the image, where, because of optical effects, image resolution can decrease. And you can do this either by making a pattern such as the one shown here that has the bar patterns replicated in the corner, or by moving your target around and moving the one bar pattern into the corners. However, In the corners, you need to measure the resolution in two directions. One direction is tangential, and that is, imagine a circle centered at the center of the image, and a line tangent to that circle is passing through the bars. The other direction is the radial direction. A line coming out from the center of the image passes across the bars. In optics, that's called the sagittal direction. Now, just for a demonstration, I'm going to increase the magnification of the display. Now, what you can see here is that we're able to resolve all of the dark bars in the finest pattern. And now I'm going to attempt to move the pattern by just about a half a bar width. And let's see what happens to the image. I'm just going to slide this ever so slightly. What you notice is that those bar patterns now blur into a single gray level. That demonstrates that you really cannot rely on the vision system to resolve something as small as those bar patterns, which in effect is the pixel size in the field of view. You can also buy commercial resolution targets. These are especially useful for smaller fields of view. Whichever target you use, make sure that you record the limiting resolution, and also save your vision system's image of the resolution target for future reference. Now you know about benchmarking imaging resolution, let's return to the lab to see about the next benchmark measurement. Closely related to resolution is depth of field. The depth of field is that distance of object distance variation in which the image still appears to be sharp in focus. Now there's two ways to do this. One way uses a fixture with a ramp with a graduated scale on it, and the other way uses a target, the resolution target, with spacers. Here's a commercial depth of field target. It's a triangular shaped fixture with a scale on its hypotenuse. You place this in the field of view and you can observe where the scale is within focus. Here's the image of the depth of field fixture. You can see in the image that there is a range of graduations that are clearly resolved. Those here in the middle. The ones above are blurry, and the ones that are below are blurry. So there is a certain range in which the depth of field is acceptable. You would record this image along with your depth of field measurements in your notes, and make sure and save a copy of this for future reference. Way to verify the depth of field is to use your resolution target along with some spacers. Start by placing the resolution target at the furthest distance away from the lens. Using the image captured by the vision systems, verify that you still have adequate resolution. Then take the first spacer put it under the resolution target. This should move the resolution target up to the nominal working distance of the vision system, and verify again that resolution is still within requirements. And finally, take the third spacer and place it under the resolution target. This should move the target to its closest working distance that you require, and you're going to evaluate the image on the vision system to make sure the resolution is acceptable. Of course, you'll save these images for future reference. Now there's even a third way to verify the depth of field on a vision system, And that's in the event that the vision system is mounted to a robot or other mechanism. In that case, you can use the programmability of the robot to change the working distance of the camera throughout its depth of field range. We move from benchmarking the image towards benchmarking the illumination. One parameter becomes immediately obvious. We need to benchmark the light level or the intensity of the illumination. There's two ways to do this. The first way involves using a commercial light meter. Now take the light meter and its sensor, which may be part of the light meter or it may be a separate probe, and put that sensor in the middle of the field of view. Make sure that you can repeat this position. Now make two measurements, one with the illumination on and one with the illumination off. Record both of these values, including the difference in illumination. That will tell you how much illumination is being provided by the illuminator and how much is due to ambient light. Now you're going to make a record of this, but remember, if ambient light changes, it may change the performance of the vision system. The second way to benchmark illumination is to use the vision system itself. Place a reflective target in the field of view. I like to use a target that's made for photography. You can also use a sheet of copy paper, but remember, copy paper reflectance isn't controlled tightly. Now capture an image of this white card illuminated, making sure that it is not in saturation, and record the level that you observe. You can also make this measurement with the illumination turned off and just ambient light on, and that again will give you the difference. When using the vision system to make illumination intensity, keep in mind that cameras have a sensitivity range that can be as much as 2 to 1 from camera to camera of the same make and model. So if you need to replace the camera and then benchmark the illumination, you'll have to reset your illumination. You can reset it not by changing the aperture, because that will change your depth of field and your resolution, but by changing the illumination intensity, the light output itself, or by changing the gain or the exposure time. In benchmarking the spectrum of the illumination, you can use a color chart like this from Graytag Macbeth. Put the color chart in your camera's field of view and image those colors of interest. Place a window over the particular tile and calculate the average gray level in that particular swatch. Make sure that you note which swatches you use and what the average gray level is for each swatch, though you can come back and duplicate the measurement. When a color chart isn't convenient, you can use other colored items. Just make sure that their colors are stable over time so you can repeat your benchmark. Some people have found that colored ceramic tiles work very well for color benchmarking. Another very important property of illumination is its direction. The conventional way in machine vision for benchmarking or characterizing the direction of illumination is to use a polished sphere. Place the sphere in the field of view and image it with the camera. You will be able to see where the light is coming from as it reflects off of the sphere into the camera. Now there is distortion, but this will still work as a good method of characterization. And examples of spheres that you can use include small steel balls ranging from 1 millimeter in diameter up to 2 inches in diameter, a Christmas tree ornament, a moon dish hubcap, or a gazing ball. The vision system's monitor shows the image of the ball. The illumination is reflecting off of the ball and can be seen here along the line of illumination, and its position can be judged by the position on the ball. Now, I happen to be standing between the sphere and a window in the office. If I move aside, you can now see the reflection of the window appear. So the sphere will show you not only the engineered illumination, but any ambient illumination as well. Make sure you record this image and print a copy for your notes. Here are some other images of light reflecting off of the steel balls. You notice from left to right, we have 2 point sources on opposite sides of the camera. Then we have a ring light, and then we have a coaxial diffuse illuminator. Now we turn our attention to the final but very important step of benchmarking illumination uniformity. Although we call this illumination uniformity, and the actual illumination uniformity is fairly significant, there are also other factors at work here. For example, the lens's light gathering power changes as we move away from the central axis. It decreases approximately proportional to the cosine to the 4th power of the angle. Also, the sensitivity of the image sensor varies across it up to 10%. Now, to perform this benchmarking, you'll do some image processing that isn't very complex. It's likely you can do that on your vision system, but if you can't, that's okay, because you're going to capture the image and save it anyway, and you can go to an offline program such as Photoshop or the free program ImageJ to do the processing. Oh, and if your vision system has uniformity correction, also called flat field correction or light leveling, where each pixel is multiplied by an individual gain factor, you'll need to disable this for this benchmark. In the lab, I'm going to show you how to benchmark illumination uniformity. Place a white card in the field of view, acquire an image, and save that image. Some of the more advanced systems offer the option of a pseudocolor display. In this display, each gray level is assigned a color. Now, before you do this, you'll need to heavily filter the image to remove all noise, and then assign a color to from 2 to 6 adjacent gray levels. The result you'll get is going to be similar to what's shown on the slide here. Another way to get an image that reveals the uniformity of illumination is through a series of processing steps. First, filter the image. I like to use a median filter with the radius of about 15. If you skip this step, or even if you perform this step and your image is excessively noisy, the result you'll get will be very hard to interpret. Second, decimate your image. Reduce the number of gray levels from 256 down to, say, 64. This means every group of 4 gray levels in the original image is replaced by 1 gray level in the resulting image. Next, make a copy of the decimated image. The 4th step is to erode that decimated image with a 3x3 structuring kernel. 5th, subtract the eroded image from its decimated original. And the final step is to threshold that difference image with a threshold of 1. This will reveal a series of contour lines called isophot lines. This illustrates the result. The isophot lines resemble contour lines on a topographic map. Now, since we decimated the image from 256 to 64 gray levels, each isophot line represents a change in the original image of 4 gray levels. In practice, for most vision systems, an illumination uniformity of 10% or about 25 lines out of 256 shades of gray, is about acceptable. In our illustration here, that would be equal to about 6 isophot lines. Now, regardless of whether you use the pseudocolor or isophot technique, make sure you save both the original and the processed images in your notes. Well, we talked earlier about uniformity correction, also called flat field correction or light leveling, and you turned it off for this benchmark. But wouldn't it be good to know how well it performs? Well, it's very simple. Enable it and calibrate it if necessary, then reperform the uniformity illumination test, the exception being that you shouldn't need to filter the image quite as much, and you don't need to decimate it. If your vision system's uniformity correction is working well, you'll have only a few colors or a few isophot lines in the resulting image. While there are machine vision applications that aren't affected by optical distortion, vision systems that make measurements are affected by optical distortion. Distortion may be caused by the lens itself, and it may be caused by the camera not pointing perpendicular to the field of view. Vision systems that do make measurements often or usually provide for the correction of distortion by using a target that commonly consists of an array of dots, or in some cases a checkerboard pattern. Follow these steps to calculate your lens's distortion. If your system provides distortion correction, it almost certainly provides you with a table listing the centers of all of the dots. Copy these centers, coordinates, both X and Y, into a spreadsheet. This may take a little bit of typing. Now, if your system doesn't have distortion correction, then you'll need to use your vision software's blob tool to find the centers of each of the dots. Copy those X and Y coordinates into the spreadsheet. Now, using the spreadsheet, find the spacing between each dot's center and its neighbor immediately to the right, and each dot and its neighbor immediately below. For all of those distances, find the maximum and minimum value. The lens distortion is the difference between the maximum and minimum divided by the sum of the maximum plus the minimum. The next benchmark is to characterize the imaging noise. Follow these steps. Using a light background, capture an image, but make sure that the image is not in saturation. That is, no part of the image has a grayscale that's the maximum allowed by the vision system. Now, without changing anything, capture a second image. You're going to save both of these images. Now take the absolute difference between those two images and scale that difference image. For a low noise vision system, you may have to multiply that image by a factor of, say, 100. Now look at the intensity histogram from that scaled image. That will give you a good idea of your noise. If your vision system doesn't perform the calculations, you can take those two saved images and use an offline program like Photoshop or the free program ImageJ to make those calculations and display the scaled histogram. Here's what the noise image looks like. Also shown is its histogram. You want to make sure that in addition to saving the original images and the processed image and histogram, that you make careful note of what scaling factor you used. And remember that the imaging noise is not just image sensor noise, but it's also noise contributed by the power supply, noise contributed by image digitization, and noise contributed by the light source, for example, through flicker. Now let's return to the lab for our final imaging benchmark. Here's the image of our part. Also shown is its intensity histogram. Save both the image and the histogram, if possible, to your CD and print out a copy of both for the binder. Now you know 10 important measurements you can make to benchmark your imaging. Using these, you can move forward with your machine vision work, confident that if problems do arise, you can quickly and efficiently pinpoint the source of the problem and get it corrected. Most importantly, don't forget to keep a copy of all the images you've acquired and processed on a CD, and print them out and keep them with your notes so that you have a permanent record you can refer to. Now you're ready to ensure the reliability, reproducibility, and maintainability of your vision system.